Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today we're glad to have Sheldon Zhuang from UIUC to give us a talk on audio-visual event detection. Sheldon is a PhD candidate at the UIUC. He got his master's degree from electrical engineering at the UIUC in 2007 and a bachelor degree from Tsinghua University in 2005. So without further ado.
Thank you for coming in the morning. So today I'll talk about modeling audio and visual cues for real-world event detection. This is the topic I picked for my dissertation as an umbrella to include a couple of projects I got involved over the years. I also prepared a couple of snapshot slides towards the end, just covering a couple of other projects I was involved in that might be interesting to this audience. So audiovisual event detection aims to identify semantically defined events that reveal human activities. I agree we'll all agree here that while speech is the most informative information source in the audio stream, and a lot of the non-speech events also tell you what's happening in your environment. For example, on the acoustic side, if you have events like door slams, steps, chair moving, key jingle in this room, they tell you something about what's happening. And in particular, if we hear a very loud yawn here at the very first 5 minutes of the talk, then that's also something that tells you a lot about the talk. We also know for the video events, it's also very apparent that if you can figure out what's happening in the video, it makes uses to multiple applications like surveillance, human-computer interaction, supporting independence and well-being of agent population, video annotation, and multimedia retrieval in general. As useful as these applications are, they are relatively less studied than speech recognition. It's also a shorter history for these applications. But they are explored by different researchers before. For example, many people worked on detecting restricted highlight events, such as a gunshot in a street, or explosion in a movie, or a goal or cheering detection in a sports game. Many times, people leverage lower-level detectors. For example, a car detector, a flag detector, an office detector, using these things for video event detection. And in particular, people, for a meeting room scenario like this, people would use a person detector, a laptop detector, face detector, and door activity estimator. And the benefits here are that hopefully these lower-level detectors are transferable between different tasks. But the drawback is that these are usually ad hoc and need more annotation for training. So in this work, we're trying to see what could be a generalizable and robust way to model these cues for detection of real-world events. By real-world events, we're meaning events that come from data that are realistic and that are not collected in a lab setting. So my talk will be roughly into three parts. The major pieces are actually the first two parts. First, I'll talk about classification detection of acoustic events. There's a lot of lessons learned from the speech recognition community that actually, I think this audience will find a lot of the methods very similar to what we use in speech recognition. And they work so well because they survive all these decades of work in speech recognition community. So to detect and classify acoustic events is a task of significance. According to the clear evaluation that we were participating, the activity detection and description is a key functionality of perceptually aware interfaces working in collaborative human communication environments. And these events usually help described human activities. So the particular data set that we worked on have over 12 events, such as door slam, steps, chair moving, key jingle. They are different. They are difficult because we are talking about a set of general events in a very realistic environment. We're not talking about a particular very highlight events like explosion or something like that. And also, the temporal constraint between different events is much looser than in speech. There's no linguistic constraint, of course, and usually they happen. They don't tend to happen following a particular sequence. The SNR is low. The particular data set and setup we use actually was using one far-field microphone. So we haven't we haven't included any beam search and any microphone array beam search in this setup. So the far-field microphone would have background noise and also some background far-end talking speech as a background. We propose leveraging the statistical models proven effective in the speech recognition literature. In particular, we use a tandem connectionist HMM approach to combine the sequence modeling capability of the HMM with the context-dependent discriminative capability of an artificial neural network. So here we're talking about one HMM for one particular event. So for 14 events, we'll have 14 HMMs. And in a rescoring stage, we'll use a support vector machine Gaussian mixture model supervector approach to use this noise adaptive kernels to better approximate the KL divergence between feature distributions in different audio segments. We'll cover that in a while. So the way that we formulate acoustic event detection is exactly the same way as in speech recognition, in particular as a whole word sequence recognition. So you're basically maximizing the joint distribution between the observation and the event sequence. And for feature representation, we're looking at sliding window-based sequence of local frame-based features. So temporal segmentation is one of the major challenges for this problem. People have tried different ways to address this. For example, you could do super sliding window-based approaches, basically detection by classification. People also come up with ideas similar to a cascade of different sliding windows, try to improve accuracy. But from what we found and also from what the results of the evaluation says, using the Viterbi algorithm of HMMs compute simultaneously optimal segmentation classification of the audio stream. So this is still the best choice as we believe, and we illustrate this in the evaluation. In particular, we believe that the benefit is that the noise in these individual frames will be alleviated by this learned prior of preferring self transitions rather than non-self transitions in a hidden finite state machine. And how do you model the temporal context, and does that matter in this particular application? We explored this question by using artificial neural network to observe a larger context window for each hidden state. In particular, the feature vectors are observed in the context window, and the output of the neural networks are the posteriors, which are transformed and then fed into a dynamic Bayesian model, in particular a hidden Markov model. So this is also learning from the speech recognition community, but it's not always working in speech recognition because I think people having these lessons saying when the task is of low SNR and also when the models are relatively context independent, then this tandem approach usually would give you more pronounced improvement. And these two assumptions do stand true for our application because the SNR is indeed low, and also the models are less context dependent because we don't really know whether this is there's nothing like in the triphone speech models where you have a very rigidly defined context. So basically, we'll take a larger window of these frame-based features and take the output of the neural network, transform, and use that as an input to the HMMs. Another question is the temporal structure very important or not? So because up to now we use the HMMs to model the events. In particular, the HMMs are of the topology of left to right. So, so what we do want the different state sequence to capture the temporal structure within each event segment proposed. However, there's an alternative way to look at these audio segments. The audio segments, they vary in length, but in a sense, they are all a set of local frame-based features. So looking at an audio segment, whatever length it is looking at the joint distribution of all these frame-based feature vectors. So the way that we did here did also have success in speaker ID and language ID. So the idea here is to look at the audio segment as a set of these local descriptors, and then we would approximate this joint distribution using a Gaussian mixture model. And then the parameters of the Gaussian mixture model would be used to construct a supervector, which becomes this uniform length vector representation for the audio segment that varies in length. And once we have this vector representation, it can be shown that this vector representation put into a linear kernel actually approximates the KL divergence between the different audio segments. And the kernel can be used in whatever classifier of your choice. So in particular, the JMM supervector is the normalized stacked mean vectors from the different components. And it can be shown that the KL divergence between the feature distributions can be approximated by the Euclidean distance, which is why we can use a linear kernel. And there are some assumptions behind these being true. In particular, when we need the different Gaussian mixture models to be obtained by adapting from a global model. So, the scenario here is that we'll train a UBM or global model using these frame-based feature vectors from all audio segments that we have available in training, regardless of their categorical labels. And then we'll adapt this global model into each different audio segment. So it's adapting to each different audio segment instead of adapting to each category. So in the end, you have one Gaussian mixture model for one audio segment. So we're using this Gaussian mixture model as the approximation to the joint distribution of all local descriptors within one segment.
How long is your typical segment?
The segment here we're talking about usually varies from 1 second to 10 seconds. It could sometimes be shorter depending on the particular events. Like footsteps usually are pretty long, but door slam are shorter, and key jingle are not very long as well.
Okay, so that adaptation, you don't really have a lot of data.
Yeah, so for adaptation, we're doing map adaptation in this experiment and with some conjugate priors. Yeah, roughly the more data you have from each segment, the better the adaptation will be. So as you may have noticed, for this approach, we actually do need some predefined boundaries. So the way that we get around this is to have the first parse being the HMM-based Viterbi decoding, and then use the hypothesized boundaries. With the hypothesized boundaries, we'll be able to approximate the joint distributions here. So in the end, we'll have map decoding, which is Viterbi decoding of HMMs. And then with the hypothesized boundaries and event labels, we'll do confidence rescoring based on the classification result out of the JMM supervectors. And in the end, when we're combining the two hypotheses, it also opens this possibility to refine the output result according to the particular metric of your problem. So in this case, the AD metric I mentioned. So the AD metric is basically the F-score between the hypothesized event sequence and the ground truth event sequence. So they'll give you something complementary to what map decoding finds you. A very quick go over of some of the results here. So this was on the CLEAR 2007 acoustic event detection data. There are 12 general medium non-speech events, such as keyboard typing, cough, and chair moving. So basically, we could improve the baseline result, which is the HMM-based result that we submitted to the evaluation, by having a better temporal context modeling through the tandem model, and also as to harness this complementary information from a GMM supervector model in the rescoring phase here. So this is saying even if we don't have this very rigid temporal structure captured by the hidden state sequence, there is at least some complementary information coming from looking at audio segments in a different way. And the two things are kind of additive each other that could further improve your result. So then I'll talk about our experiences in categorization and localization of video events.
Question before we move ahead, could you briefly mention that what kind of features you use?
Oh, the features here, yeah, I didn't talk about features here, but if we need some result tomorrow, I just recommend using MFCC or PLP. The particular features that we used was kind of engineered toward this task. In particular, we bring together MFCC PLPs and filter banks with different parameters. So build a pool of kind of well-engineered speech features, and then we select some of the, and we decorrelate these features and select a subset of the features out of the pool according to some boosting-based method or according to the Bayes arrow for individual features. Yeah.
Do you use like zero cross and that kind of features?
We haven't used that. We have other participants actually use that.
Yeah, so I just wonder if you...
Yeah, we haven't explored this in particular. And frankly, I have to say the reason that we performed better than the other participants, we don't have proof saying that it's on the feature side whether we're doing better or not. We believe it's more on the modeling side that we're doing everything right and in a reasonable way that give us an advantage. Yeah, but we
mainly rely on MFCC features.
Yeah, or we kind of derive features out of the pool that consists of MFCC's filter banks and PLPs. The major motivation that we want to leverage on what the community has accumulated over the decades, and we believe these features are the best choice if you have limited time. So.
In your work, you use the temporal information in your model, HMM model, and the tandem model, right? Another way to think is to have a multi-scale, temporal scale features. Mm-hmm. So you haven't tried, I guess.
We haven't explicitly tried in that regard. I think the only way to say that we might have some kind of multi-scale temporal thing happening here is in the first parse, the HMM has this neural network to observe a larger context. While in the rescoring phase, we just use the local frame-based features. But it's complementary in different ways. One way is that it does not have this rigid hidden state sequence. And also, as I said, the GMM supervectors observe directly the frame-based features, not with this wide context window. Okay, so move on. So I talk about categorization, localization of video events. This is centered around an improved image and video representation called Gaussianized vector representation. But as we go on, I think this audience will find a lot of these things very similar to what we just saw from the GMM supervector, because it's just we are actually inspired by what's happening in the speech and audio models to see whether we can look at image and videos in a similar way. So in particular, the Gaussianized vector representation is our attempt to say, can we model images and videos without explicitly worrying about segmentation or particular object detection within that image? So the Gaussianized vector representation adapts a set of Gaussian mixtures according to the set of patch-based descriptors in an image or video clip. And the adaptation will be regularized by a global Gaussian mixture model, and also the final linear kernel will be improved by within-class covariance normalization. And because of the success that we had in doing works like categorization and regression, we're thinking what would be a reasonable way to apply this representation for object localization. So in the end, we adopt an efficient branch and bound search scheme, and this could be potentially used to identify regions of interest in the video corresponding to different events. So one of the major problems in computer vision, probably in any of the machine learning problems, is that you want to find the correspondence between a data set. So if we're looking at different faces here, we could easily see that if you want to compare the different faces, you probably want to compare eyes to eyes and mouse to mouse. But if you look at some more realistic images, like a bedroom image or a broadcast news image, even if we see the bedrooms probably both have a bed inside, but it's less apparent what kind of particular correspondence we should find between the two images. And if you look at a video, the broadcast news video, even if this event is categorized as car entering, we don't necessarily see a very complete car in the image. So that makes any efforts based on detecting a particular car very challenging and if doable at all. So visual cues for real-world events, they present extra challenges for correspondence compared to some other tasks like face processing. So the way that we look at image and video modeling is to look at them as a set of local patch descriptors. A patch is a very small region in the image in the original spatial domain. There are two major ways that people have used to extract patches. But first way is that you would do a 2D sliding window called a patches extracted from a dense pixel grid, and then for each patch you have some descriptor based on that particular patch. Another way is to have some kind of low-level detectors. For example, a sieve detector would actually find regions where there is contrast or edge, basically something, hopefully, bear those information. But in the end of the day, you all get a set of local descriptors anyways. So the image or the video clip becomes a set of local descriptors. The most popular way to deal with this set of local descriptors is called a histogram of keywords. Basically, you have k-means clustering to establish a codebook, and then the histogram of the counts for different codebooks, codebook entries becomes the information that you carry for that image. So a very complex image like this or a video clip like this will become a histogram in the end. There's large quantization errors and loss of discriminability. So we're trying to see what can we do to improve beyond that. And I have to mention that there is improvement over the histogram of keywords itself. The way I present here is kind of a simplified version of different things. The way that we address this problem is that we still start from the set of local descriptors in the original feature space. And then, same as in audio, the information that we need from the image or video clip is basically the joint distribution of all these local descriptors. So to be able to approximate this joint distribution and hopefully be robust to noise, we'll use a Gaussian mixture model to fit this local descriptor ensemble. And then in the end, you'll have the Gaussian mixture model that approximates the joint distribution here. And then looking at different images is nothing but looking at, it's nothing bit different from looking at the different Gaussian mixture models, each corresponding to one image. And in particular, you take this normalized means of the Gaussian components to form a supervector, each corresponding to one image or video clip.
So you also, just like what you did in audio, you have a UVM first?
Yeah, so you need to have a global model so that your the KL divergence can take this simple form.
So do you adapt it to each image?
Adapt to each image or each video clip. So we use this for different kinds of scenarios. One is for each image, you have a set of local descriptors. The other is for video clip classification. You basically have a set of local descriptors extracted from all the images within that video clip. But we haven't worried about the temporal structure of the different images sequence within the video clip. So yeah, so we have a global model that's trained using local descriptors from all kinds of images and videos available to us, regardless of their categories. And also the adaptation is done using local descriptors extracted from one image or one video clip. And adaptation can be done with the conjugate prior just to help establish this correspondence with the original global model. So. And it can be shown that the distance between the two images or video clips can be characterized by the approximated KL divergence. And in particular, you could see if you write this stacked mean normalized in a proper way, the KL divergence can be approximated by the Euclidean distance. So the kernel function here takes an interesting form. It's linear, but each of these phi here is actually usually of very high dimension. So in our experiments, we would easily take 500 Gaussian components for broadcast news video. And maybe for simpler data set, you could take a smaller number of Gaussian components. But because it's linear, so it's less a problem computationally. To wrap up on this part, so the Gaussianized vector representation has a couple of advantages compared to the original histogram of keywords representation. First, the assignment into the different keywords is replaced by a soft assignment to the different Gaussian components according to their posterior. And then we could leverage the Mahalanobis distance instead of a Euclidean distance, although for this representation, the Mahalanobis distance can be written as a Euclidean distance if you have this normalized properly. And also, the multiple order statistics are taken into consideration. In particular, compared to only the counts, which is the zero order statistics, we can also use the adaptive means and also take into consideration the covariance matrices. So a way to visualize this is in place of the very simplistic histogram of keywords representation, the Gaussianized vector representation would not only establish the correspondence through the different Gaussian components as the hubs in the 2D visualization, but also according to how well all these local descriptors are adapted into these different modes and what their distribution is around the different modes. So a kind of a diversion from here is that the way that we do this is saying we don't want to establish any hard segmentation because it's very hard for realistic data. But we're basically leveraging only the Gaussian components to give us that kind of correspondence. But if for kind of data that is very structured, like a human face, can we use something beyond the mixture of Gaussians to set up this correspondence? The answer is yes. One way to do this is, one most straightforward way to do this, I would say, is to use a hidden Markov model. And for example, we tried on face images. If you take a hidden Markov model, even if a very simple left-to-right hidden Markov model, if you arrange your local patch descriptors in a scanline style, such that you would observe first the eyes, and then the nose, and then the mouth, then a very simple left-to-right HMM would give you some additional performance improvement because the hidden states here kind of capture the temporal structure that's very structured with face images. And this is not usually true for broadcast news or general video, but for faces they're true. Another way to look at why the Gaussianized vector representation had very good practical performances is that if we do some approximation and look at the feature in such a way, first we can calculate the posterior of an observed patch coming from the case mixture, and then we can randomly distribute the observed patch into m Gaussian components or classes by a multinomial trial according to the posterior probability. So in the real world, we're doing map adaptation, so it's kind of a weighted summation. But if you look at it as a multinomial trial, then you would be able to write out the equations and see that the final supervector actually observes a standard normal distribution. So this has a benefit because a lot of the later processing for computer vision usually take this as an assumption. For example, if people need to do PCA to reduce dimension, people need to calculate distance in the Euclidean as a Euclidean distance. All those processes are assuming that the feature vector lives in a Euclidean space. So this representation is partially to satisfy that assumption. So we believe this might be the reason why it will give you performance boost. So up to now, we have used no categorical supervision for deriving these representations. Of course, you can use the kernels in an SVM, then introduce this supervision. But before that, we would like to do something else to leverage the categorical labels that are so expensive to obtain in the first place. In particular, we use within-class covariance normalization to identify a subspace for the kernels that has maximum inter-image or inter-video distances within the same categories. So basically, this term here is calculating the distance between different images if they are coming from the same category. And in the end, you get this covariance of these, the covariance that contributed from all these pairs that come from the same category. The refined Gaussian vector kernel would suppress this undesired subspace because it tells us nothing about the target category labels. So in particular, we can suppress that subspace by subtracting it from the original identical covariance kernel matrix here. So we're comparing this with the then state-of-art a paper working on a video event categorization retrieval. So this is a paper that was given the best performance for this particular task, but it was also a very representative way of how the computer vision community looks at these problems. So the particular way here is that they are dividing the video clip into subclips in a hierarchy. So you have so this is one video clip, and the other is another one. So the essential problem is how do we characterize the distance between the two video clips? So the way many people look at this is that I want to find the correspondence between the two video clips. So I want to see which frame corresponds to which frame. This is temporally, but potentially you could also do which local descriptor corresponds to another local descriptor spatially. That's the same idea. So in particular, you could establish a kind of hierarchy to look at this video clip at different temporal resolutions. And then you try to find pairs between the grids in the different video clips to establish this correspondence based on some optimization. And then once you establish that correspondence, hopefully when you calculate the distance between the two video clips, your calculation is to compare apple with apple and pair with pair. However, we're showing that even if you don't have that explicit step to do this computation, you could also get reasonable and even better result using something like the Gaussian X vector representation. So in particular, we're comparing, we're using the Gaussian X vector representation with different classifiers. We could show, even with the nearest neighbor classifier, it's actually performing pretty well compared with in the TAPM approach. People actually use the support vector machine. So if we combine the Gaussian X vector representation with the support vector machine, that gives you an even more pronounced improvement. And also, we could get benefits by taking within-class covariance normalization to refine the kernel in this supervector space. Another.
Where's the result with this kind of video alignment?
This is the TAPM result, the temporally aligned pyramid matching.
So you didn't,
develop on top of that?
No, it's a separate thing because we actually didn't worry about the explicit alignment between the images, and we believe they actually did find the alignment sometimes makes sense, but not always. So I think the idea here is not to say we don't want to any alignment in the end, but we want to say if the alignment is very hard to do, can we do something reasonable such that even if we don't do alignment, we can perform comparably? The answer seems to be we could perform even better on this particular problem. So that's one of the reasons we think this is a result that we're very excited about, and we proved this similar findings on different applications.
So basically, the alignment, event correspondence information that they report, you haven't integrated into your system.
No.
So do you think if you one day you integrate that on top of your results, you can get better?
This yeah.
Or you already have used some of that concept.
Yeah, we could have already harnessed some of these information. This is a similar problem like if we do it in our way, only using the GMM or using a multi-state HMM. Do you think the multi-state HMM always would be better than the single-state GMM? The answer is maybe not always. So for phase processing, where there's a very strict temporal structure, and this temporal structure is easy to capture, right? Using left to right, you can capture part of it. If that's the case, then probably a more complicated model would actually do you good. But for broadcast news, because from their experiences, the found correspondence are not always what they intended. So we're not sure. Maybe a version of that combining with ours, there is always a chance to improve. But the idea of doing segmentation in the first place sometimes could be a dangerous one to do. It's just like, do you always want to do speech recognition by kind of doing phone sequence recognition first and then try to get that into whole word sequence? It's a similar philosophy. But we did use some of the other alignment methods that are popular with the computer vision community. For example, they would do a hierarchical pyramid over the spatial domain and try to take some assumptions. For example, the left-right corner probably also corresponds to left-right corner in another image, things like that. And in some applications, we actually do find improvement for that.
So for this task, there's just one event per video?
No, this for this one, yes. Yeah, for this one, we're essentially assigning labels to each video clips. Yes. Yeah.
So it's been sort of segmented.
Yeah, exactly. Yes. Yeah. So we do have a side benefit, which is because we look at this image and video as a set of local descriptors, so it's less prone to occlusion. So even if you occlude, even if you only use 20% of the local descriptors, your performance don't drop much. But there is a warning here because this 20% is purely randomly sampled. So if you very carefully occlude all those important local descriptors, then they probably won't work as well. But just as a note here, if you randomly sample 20% of the local descriptors, the result will be pretty much intact.
So you mentioned that in the feature, you only use a safe feature, right?
Yeah, in this one we're using
So
safe
you
feature.
don't really use any sort of the motion feature at all?
Not for this one, no. Yeah. We used some other features for other tasks, but the idea of this modeling backend is similar. So we want to see, can we use, because it gave us a lot of advantages in doing categorization, retrieval, but all these things are talking about the global information based on the whole images. So can we do something similar for localization, which define the particular object within an image and tell how large they are? So we adopt a branch and bound scheme that has been proposed by Lampert to allow efficient object localization that achieves global optimum with n squared instead of n fourths. And also, this scheme has been successfully applied for histogram of keywords, so that gave us a way to preliminarily compare with what other people have done using similar approaches. So in particular, the branch and bound scheme, regardless of the detailed nuances here, the basic idea is that you want to search all these n power to the 4 rectangles, but not one by one. You want to throw out sets of them if they have a very good bound to tell you what the upper bound for that particular rectangle set is. And if the bound is worse than the bound of another set, then you can always start with the set with the highest bound. And then if the bound is good enough, then you won't miss the target rectangle that you're hunting after. In particular, you would initialize an empty queue of a rectangle sets and initialize this a rectangle set to be all the rectangles. So if we characterize this as top, bottom, left, and right, the set R initialized as all rectangles are having the top, bottom, and left, right to be complete scale for each of these dimensions. And then we would obtain two sets by splitting the parameter space along the largest of the 4 dimensions. Then you would push these two rectangle sets into the queue with their respective quality bound, which we'll talk about in a minute. And then we'll update R by saying we'll look at the set with the highest quality bound. In the end, the set would shrink, and in the end, it will become only one rectangle. That's the one that we are trying to find. Okay. So in order to introduce the quality bound, we'll first talk about the quality function here, which is informing the confidence of the evaluated subarea being the target object. So we're actually using the output of a binary SVM, just in a standard format. So the bound should satisfy 2 conditions. It will be larger than any of the quality functions evaluated at any of the member rectangles. And also, if the set becomes one member only, then the bound should be equal to the quality function evaluated on that single member. So you can see, first we can see the quality function can be rewritten with approximations as the summation of some of the contributions from each local descriptor. So in particular, define this per feature vector contribution here. So in the end, we'll know this. If you are to evaluate a particular rectangle, that's nothing more than evaluating the summation of the contributions coming from all the member patches within that sub-area. So if we can written it in this linear format, then the quality bound can be written as the summation of the positive local contributions from the largest rectangle plus the summation of the negative contributions from the smallest rectangle. So this one is to evaluate the quality bound for a rectangle set. So that's essentially all these positives coming from the largest member and all the negatives coming from the smallest member. And it will be easy to verify this satisfies the 2 conditions that we just set forth.
Since you already have this GMM modeling, so for every vector, wherever is a feature point, computer like with respect to class. So you could use that as score instead of doing this.
So this is so you're talking about how this per feature contribution is calculated?
There's an alternative of doing feature vector contribution, right? For each feature vector or basically for each feature point in the image. Because you're already modeling GMM anyways. Because the other people in object detection, they do that because they don't model that. They don't use GMM to model them. But you already use GMM to model it, so you could compute the likelihood for each
Gaussian component, right?
Each vector, right?
Yeah. We use the Gaussian mixture models to approximate one distributions for one image and one video clip, but there's no class information. Yeah, there's no class information here. And of course, you could say, why don't we do classification based on classification of each local descriptor? But I'm pretty sure that will not work because a single local descriptor is very noisy. So if we want to do classification based on that, then it's usually not working as well. So we are using the Gaussian mixture model to approximate all this distribution within one image, and to hope this smooth distribution modeling can actually suppress some of the noises coming from the local descriptors. So that's why. But if you look at this per feature vector contribution here, that's what I was about to say, is that the calculation of all these things are essentially the same as calculating the adaptation of a global model into this particular image with all the local descriptors. So because the per feature vector contribution, it seems you need to do this for all the local descriptors. But that's the same thing as doing adaptation, where you already sum up the adaptations of each feature vector according to their posteriors to different Gaussian components. So computationally, it's very similar. To getting the complete set of per feature vector contribution is computationally similar to doing the adaptation for the whole image, just because you could written it as approximate it as a linear way. Yeah.
In the previous, earlier, before the localization, we are talking about the event recognition, right? And that's based on comparison between video clips to another video clips.
Yeah.
So it seems not very scalable if you have a lot of labeled clips about different events. You have to compare with all the different events, right?
Oh, so the comparison. So once we get this Gaussianized vector in place, then we'll basically just calculate the kernel matrix.
But you need to compare all the kernel matrix for each.
Yeah. Basically, you have a multi-class.
You have 1,000 or million clips. You have to compare with all, right?
Yeah, that's the same idea as if you have multi-class SVM for classification of multiple categories, right?
I think you're talking about supposedly the training data, you have 1,000 clips. In test data, suppose you have maybe 100 clips. So if
you need to compute with each of the training ones.
Right,
Yes.
right.
Exactly.
So you really don't model any event.
You model event only in the kernel space. Yes.
Implicitly.
Yeah.
Right.
You only with the kernel space you model the events.
So for example, I have car entering event, and I have 100 video clips
For car entering.
for car entering.
Yeah.
So you have to compare with all the 100.
Yes, that's right. Yeah, that's right.
But in this localization part, it seems you are doing differently. You have some model.
For localization, you're actually doing the same. So for localization, one thing that I probably should have emphasized is it's basically based on a two-class classification problem, right? It's either the foreground, the target, or it's the background. So when you have you say you have 500 positive training tokens foreground, and then you have 500 negative background images, and then so when you're training this binary class SVM, and then in testing time you still have to calculate the kernel. You have to evaluate this kernel with using the one test vector with all these training.
In this case, you have already modeled the probability, the likelihood of each feature to each event, right?
Not really.
That's,
So
that's the confusing part.
Yeah, that's what
It does
I'm
not model
confused.
the likelihood of feature vector with respect to class.
Right.
It does not model that.
So how will you do that?
So the only difference between in this regard is a binary SVM versus a multi-class SVM. So you calculate the kernel matrix, and then it's the training of the SVM that deals with this categorical supervision. So you're always getting. So the only thing that we change here is how do you calculate the distance between two images? Yeah, so you're still looking at this kernel matrix, which is always looking at two individual images, one coming from the training and one coming from the testing.
And in the training, you have already labeled the regions.
Yeah.
I see.
So then your SVM is sort of the.
Yeah, SVM is the way where the supervision comes into play.
That's really where you sort of you use your possible data would be the foreground objects.
Yeah.
And so the feature vectors that are located on the foreground objects.
Yeah.
The rest of the feature vectors are the background, or the negative data. Then you train the binary classifier.
Yeah.
So that's sort of you don't really need the separate the classes. You just do you do this SVM per event per class or one to many like for car entering you have one you train the SVM and then for another type of event you train another SVM. So how you do it?
So the way that we do it practically is that we get this one super vector, this vector representation for one image, right? So for each let's first talk about the video event categorization problem. So we have one vector for one image, and then we also know the label for that vector. Then we throw this into a multi-class SVM training program. So for localization, we have different images. Some of these are the target, some of these are the background, and each of them would be converted into a vector, right? And then we throw this into a binary SVM.
Okay, so then it's not the same as you do the kernel. You don't need to do kernel anymore.
But when you throw it into the binary SVM training, you basically throw the kernel matrix in, right?
Sure.
Yeah.
Sure.
So.
But then, I mean, you're saying that you classify it, it's not just to compare.
The distance distribution. It's not to compare.
Sure, the classifier itself is supervised. So
Yeah. So that's
SVM.
So this is a bit different from what you did before. So in terms of localization, I mean, you did the categorization experiment, right? And that experiment, the way you do classification is different from here.
So for localization, the core is the binary classifier, but for localization, the problem is that you have to do binary classification for many hypothesis rectangles, right?
Yeah.
So the way that it looks different here is just because you organize it in this linear summation, so that you can reuse a lot of the computation, and also you could bound this subset of hypothesis rectangles and then throw them away if their bound is bad enough. But at the core, it's actually a binary classification. It's to tell whether this sub area is the foreground or background. So in that sense, it's the same as the video categorization, where it's a multiple. Okay. Here are some examples of how things look for localization. So basically, you would identify the areas correct if you collect this local positive red areas and less of these negative blue areas. And sometimes it goes wrong because the red areas are not as clustered together as we want, or sometimes we count it as a wrong detection when you combine two cars into one model. So we compare this with a similar work using the histogram of keywords based on this search and bound scheme. So it's consistently improving beyond the histogram of keywords. And we can also see doing within-class normalization can also further improve the result, where all these ends are meaning the within-class covariance normalization. Okay. Yeah. So I quickly go through the third part, which is relatively short anyways. So this part is trying to say acoustic event detection is very hard, and even if we did reasonably well, the performance is far from usable from a practical perspective. So people are trying to look at, can we engage video to help, just as the way that we engage lips to help speech recognition. So for the previous work, people have proposed a detection by classification system, and that system used a lot of extra information, including audio spatial localization, multi-person tracking, motion analysis, face recognition, object detection. The drawback is that training all these ad hoc visual detectors are very expensive, and we're trying to see, can we go around this and do something reasonable such that the performance is comparable at least. So the way we look at this is that all these non-speech audiovisual events are mostly related to motion. So we're using visual features based on optical flow. And then we are summarizing all these optical flow firings using an overlapping spatial pyramid histogram. So basically, we're looking at a complete image and calculate a histogram of the local optical flow firing magnitude. And also we look at this 2x2 grid and then extract 4 histograms. And then we'll look at this 3x1 grid and extract the 3 histograms. And then we stack all these histograms together and do the correlation and use that as a video feature vector for each frame. And that goes together with the MFCC or something like that for the audio stream. So to combine these, we use the multi-stream HMM and coupled HMM. In particular, with the coupled HMM, there's a lot of hassle to initialize such that the output PDFs becomes reasonable. So the way we tried two different schemes, one way to initialize using a state-synchronized multi-stream HMM pair, another way to initialize it using pairs of audio-only and video-only HMM.
Can you comment a little bit more coupled HMM?
Yeah, so the coupled HMM, it's basically a coupled HMM is saying the state, in a multi-stream HMM, the audio state sequence and the video state sequence would progress at the same pace. So the first audio state goes to the second, at the same time the video goes to the second. In the coupled HMM, they can go asynchronized from the perspective of the state sequence. So maybe the audio state is already progression into the second one, while the video state is still residing in the first one. But actually, you could look at a coupled HMM as a HMM with more states. But the equivalent HMM have more states because each of the states in the equivalent HMM is defined on both the audio state variable and the video state variable in the coupled HMM. So in our experiment, we're actually allowing state asynchrony up to one state, so that you don't really grow this topology into a huge structure. So in the end, it's about how do you initialize the output PDFs of the coupled HMM or its equivalent HMM. So when I'm saying we initialize using multi-stream HMM, it's basically initializing, assuming the audio and video states should always be synchronized on the state level, and then we would combine the PDF from the first audio state with the first video state, and also we have another state that's combining the first audio PDF with the second video PDF. So in that case, we construct this equivalent, this HMM equivalent to the coupled HMM. Or another way to do this is to initialize using audio-only HMM and video-only HMM, and then put their states together. And once we put together this equivalent, this coupled HMM equivalent HMM, then we can do re-estimation based on the new topology. That tends to converge easier than if you directly train on a coupled HMM. It pretty much always fails, and most of the states never get traversed. So the answer is, in terms of can we get performance similar to doing all these lower level detectors, is absolutely yes. So we could actually do better than their approach. The benefits come from, of course, multiple places. First, if you use the dynamic Bayesian model to do Viterbi decoding, there gives you advantage. And also, when you characterize the video using this generalizable feature, that sometimes might even give you advantage than to use the very localized low-level detector. Another thing is that, however, the two ways to initialize the HMM actually turns out to be not very significantly different. But as a warning is that it is important to initialize them reasonably, but which one doesn't seem to make much difference here. Okay, I think I need to wrap up here. So it's basically, I talked about audio event modeling, a lot of lessons from speech recognition, and video queue modeling, where we want to say, can we do these jobs reasonably without going all these very painstaking segmentation? The answer is yes, and in many cases we actually do better. And then we could improve the acoustic event detection by using audio-visual multimodality modeling. Thank you. It's the picture of the incomplete group. Maybe you would recognize a couple of faces who was here on this campus for a while. And I have a few very quick shots, but I think we're going over time. Should I take 5 more minutes, or should I stop? Oh, okay. Some other projects that, so just because this is a very interdisciplinary group, that the speech group and video group work very closely together, and I also had experience working with phonologists who are interested to see whether a phonological theory works in speech recognition setup, or can we devise a computation model according to their theory. So that gives me exposure to a couple of different projects that might be related to something happening here. For example, we worked on a pronunciation modeling, which basically following the articulatory phonology theory. So according to this theory, a word is pronounced as this word because there's a unique set of gestural targets behind it, defined on different tracked variables. And when the word is co-articulated with something else, or the speak rate changes, there's a speech reduction, this set of gestural targets are still there. They're just arranged in different ways. They shift along time, but the targets are still there, but because they overlap with each other in different ways, so their surface form change. So that's their theory, and we're trying to build a model according to this theory. So the way that I answer this question is if we define the gestural targets at a local time frame as a vector, then this 2D representation just becomes a vector sequence problem. So we will say a gestural score, as a 2D dimension here, defined on tracked variables in time, could be approximated as a sequence of gestural pattern vectors, each vector defined on the constriction targets at this local time. So once we have this formulation, we want to see, can we do speech observation to gestural pattern vector sequence, thus to the gestural score, therefore to words. So the gestural pattern vector would encode instantaneous patterns of gesture activations across all tracked variables in the gestural score given a particular time. And the gestural score, approximated as a sequence of gestural pattern vectors, is the example of gestural activations, which is basically the approximated gestural pattern vector sequence. And of course, at each step, we could introduce some confidence score, the likelihoods. The interesting part is actually on the gestural score to word part, where we use a intergestural timing model, which was originally developed for articulatory phonology, to generate one canonical gestural score for different words. This is like the canonical pronunciation for this word. So the words will be distinguishable according to the gestural scores in the sense that they are distinguishable according to this example of gestural targets behind them. But they are not distinguishable according to their particular timings, because when a word is pronounced by different people in different contexts, the timings tend to change according to articulatory phonology. So the computation model that we devise according to this theory is that we have a finite state machine emitting gestural pattern vector sequences. So you could imagine each parse in this finite state machine actually is emitting a gestural pattern vector sequence, which is essentially a gestural score with particular timing. So if we look at the word the here, these are the different tracked variables. So they always have these 4 gestural activation targets, but they could be arranged in different timings. And we want to summarize all this into a finite state machine through some recursive process. And once we have this finite state machine, so this machine is basically the pronunciation of this single word. And once we have this machine, we'll be able to do word recognition by composing a lattice with a pronunciation model, which is roughly the union of all these different word pronunciations.
How do you build this finite state machine? By looking at the acoustic realization, or by looking at the articulation?
We actually look at the canonical speech gesture. So we have this intergestural timing model which could generate one of these 2D representation for each word. And then we're saying the pronunciations allowed are basically all the different possible shiftings of all these gestural targets. So we're building this recursively by saying, looking at the canonical one, let's say the example of the gestural targets we have. And then at each time frame, we're proposing possible combinations of them, and then weighted by some kind of quality measures to measure whether this combination is possible or not from the training data or from their theory. So each time we're doing a interstate transition, it's like changing from a particular local gestural target combination into a next one. And each self-transition is saying will stay in this particular configuration for another time slot. So we're building this recursively as building a tree. And then in the end, you can optimize this finite state machine by weight pushing and everything. But once you get this finite state machine, you could use the open source finite state machine toolboxes to optimize and construct a dictionary. But this is still at a very early stage. It's not, we don't have any evidence to say this works better than the conventional approaches. So it's more like a interdisciplinary exploration with the phonologists.
So you built a set of detectors of
the targets.
Yeah.
So the way the part that I worked on was to devise how these things all put together. We have collaborators in Haskins labs. They were working on how do you recover this underlining 2D representation from the speech surface form. So they have actually a series of works working on that, but I think it's probably beyond what I can talk about. Yeah, another thing is we did some kind of speech retrieval for unknown language for a multimedia evaluation, where the basic idea is that you will build indexes for each database entry using you will summarize each dataset entry as a lattice and then convert that into a finite state machine based index term. So that term is basically allowing transitions from the beginning into many of the internal nodes instead of requiring a complete traversing of the one parsing the lattice. So when you're introducing these extra transitions from the beginning to the different nodes, you would associate with something like a forward probability or a backward probability. So that part we're actually just following the Bell Labs approach before. The reason of doing it that way is I was given 3 weeks to build this system, so I want to devise something that requires less tuning. So using the finite state machine was a reasonable way to do this, and the tuning could mostly be done using standard optimization methods. For unknown speech, we are talking about looking at model training with different languages, but none of which is the testing language that you retrieve from. So the idea here is that you would want to have models that are hopefully language independent. So the way that we address this is to cluster all these language dependent atomic models and then do clustering based on their pairwise distances. And then the clustering result would hopefully capture information that is shared across the different training languages, but not language specific. And hopefully that information is more transferable to a brand new, never seen language at the testing. Yeah. The last one was actually done with Microsoft. The problem was to convert from speech to lips. We had originally a baseline was HTS-based synthesis model. You build one triphone visual model for each phone, and then you could synthesize the lips from the triphone sequence, which is known before. So the question here is, can you engage audio to improve? And second, can you do lips without knowing the ground truth phone sequence, which usually can be hard to get? The answer are yes to both questions. You want to engage the audio so that you can engage the audios in the maximum likelihood estimation of the video observation, which will be which would improve beyond this visual-only synthesis. And the diagram shown here is more on the conversion side, where we don't have this ground truth phone sequence at all. The idea here is that if we are going from speech to lips, it looks like it's not always necessary to jump this huge semantic gap to find the underlying speech content. And it may be easier to not go into the speech content just because how hard it is. So the way that we address this is to use the audio-visual joint Gaussian mixture model, and then we'll select the optimized modality weight according to a development set, And then on the other hand, we want to find the visual sequence that best mimic the ground truth video sequence. The maximum likelihood is a good criteria to work with, but it's not necessarily in line with the target metric, which is the human perception. A human perception is very hard to do, so we're mimicking the human perception using the mean square error of the synthesized trajectories. So that'll be able to refine the visual Gaussian mixture model. It's kind of an extension to the minimum generation error that Microsoft has worked on speech synthesis. This was in a conversion setup. Yeah, that's all I have today. Thank you.